Hi everyone. Are we recorded? Everything is fine? Awesome. So my name is Vadim, and today I want to talk to you about mining software development history. I'm the lead machine learning engineer at Sourceit. This is a startup based in Madrid, Spain. I manage a team of 9 engineers. Also, I'm a Google developer expert in machine learning. As a matter of a habit, I always make 360 photos of my talks. So please look right here and say cheese. Awesome. And we can start. So the plan of my presentation is as follows. First, I will give you a brief introduction to mining software development history. Then I will present you 3 examples. Just never mind these names. I will explain them later. And I will finish with explaining the tooling. So there are some tools to do development mining. They are quite fun and easy to use, so I will present them. Let's go with the first part, which is introduction. I'm pretty sure all of you work with version control systems. Most likely this is Git, maybe SVN, maybe Mercurial, who knows. But Mercurial and Git, they work quite similar. You have a directed acyclic graph of your things which you store, let's say. You have commits. Every commit has a number of parents, a number of children. Also, it has metadata, such as author or committer, or the date when the commit was created. And also, the commit is actually a snapshot in Git. So it contains the full state of the repository at that point. But you can compare it to the parent and get the delta of the files which were changed in that commit. So this is a directed acyclic graph, a graph. Let's remember this. If you look inside the source code file itself, you will also discover that this is a tree. To be precise, an abstract syntax tree. Just because the way it works, if you want to make something useful with your source code, you need to parse it. And the artifact of your parsing is an abstract syntax tree, whatever you write. So tree is a case of a graph. Everything is a graph. You have graphs inside graphs, and don't be scared about that, because actually this is awesome. Graphs are very well studied, and there are many good approaches to deal with them, such as you can calculate centrality measure or any other measure on your graphs. You can calculate page rank. And this is not just, bare words. There is a startup called SourceCred. I really love it, although it's not really related to my daily job. The idea of those guys is really nice. They try to estimate the importance of each open source contributor by aggregating all the information and also running PageRank on the contributions, and pay bitcoins proportional to your, let's say, importantness. So I really like the idea. I hope they will succeed. You can embed your graphs, such as node embeddings or maybe edge embeddings. Again, the field is quite well studied, and there is just one example I want to tell you is Node2Egg. You do a series of random walks in your graph, and every walk is a context, and then you embed it. So it can capture different things depending on what you want to capture. This is the cool part about embeddings, that you can just manage them and capture the thing which you want. You can do clustering, and community detection is a case of the clustering. It's a fuzzy clustering. Again, it can be useful, I don't know, group commits together or group files together. Again, many approaches exist. You just need to apply them and find a way to apply them. Or you can go really hardcore and try to apply deep learning, such as gated graph neural networks. This is one example of that. Gated graph neural networks are proven to be able to solve the majority of computer science problems on the graphs. For example, they are proven to be able to solve the shortest path problem or do node classification. So this is very powerful deep learning model which you can apply to graphs. And it is applied to graphs, I must say. Apart from working with the graph structure itself, you can also look inside the diffs. So what was changed in a particular commit. And there are different ways to calculate the difference. Of course, you can just calculate it line by line, and this is how Git works and other version control systems. This is like the usual way. It works so well because the complexity is very nice. The Myers algorithm is linear complexity over the length of your files. This is why it's so widely popular. However, as I said before, your source code file is a graph, so you could try to calculate the difference on the graph level. And if you constrain yourself by just having two possible operations, the adding a node and removal of a node, there is no problem. The complexity will be still the same, and you calculate your graph difference quite easily. However, usually you also want to take into account the third operation, which is a move. So imagine that you have a node, you move it somewhere, maybe do some fuzzy changes, but still this is kind of the same node as you had before. Otherwise, I can easily propose you a very simple graph difference algorithm where you just remove the whole tree before and add the whole new tree after. Nobody wants this diff, it makes no sense. And it turns out that this, let's say, useful type of graph difference is NP-hard. It's proven to be NP-hard, and the state of the art in the papers is a bunch of heuristics just to try to provide the minimal edit distance for a pair of trees or graphs. So this is hard. This is why usually when you mine diffs in version control history or in your IDE snapshots, you end up with line difference, but you try to annotate it with ASTs. So whenever you have a token change, you map it to the corresponding AST where it exists. It's better than nothing, and it's more powerful than just working on regular diffs. This is a brief introduction. Okay, and now I'm passing over to 3 examples. I hope you will like them. The first is coupling. The idea of mining couples is as follows. Imagine that several developers commit to the same file quite often. Maybe something is common for these developers since they work on the same files, right? Maybe they're in the same team, maybe they have the same experience. I don't know, but this is suspicious, right? So how about trying to, visualize it or, capture these couples somehow? The second point is about files. Imagine that a certain group of files often appear together in the same commit. Maybe you edit your API and also edit the tests. Maybe you edit your high-level API and you have to recursively change other files which depend on your API. It really can be different. Anyway, again, this is something common about these files. Something is fishy. You need to look inside and maybe decide that you have to refactor, or these files often appear together just by chance. You don't know, but you need to check it. Again, we should capture this. So how do we capture this? This is a good question. And to answer it, let's revise how Word2Vec works. I guess you heard about Word2Vec. Who didn't hear about Word2Vec? Everybody? Okay, almost everybody heard about Word2Vec. But this is a quick recap. The way Word2Vec works is once you are able to build the context in which your words occur, which is naturally sentences, you can embed them so that words which often appear in the same sentence are close to each other in your embedding space by Euclidean distance or maybe cosine distance. It's not so important right now. And there are algorithms who make a series of passes over your data set to embed your words. Also, there are algorithms which work on the explicit concurrence matrix. You can build your concurrence matrix where on every row and on every column the corresponding value is the number of times these two words appeared together in the same sentence or in the same context. This is called a concurrence matrix. The concurrence matrix, let's say explicit algorithms, have a number of advantages. For example, you can manage your vocabulary size. So you can just throw away the words which are irrelevant and embed the rest. So it can reduce your complexity in some cases. You may have heard about GloVe. This is one example of an algorithm which works on the explicit matrix. There is also Swivel, proposed by Google, I think, 1 or 2 years later. I like it more because the implementation seems to be more solid. So I use it in my experiments. Let's combine this idea from word to egg and our goal to capture this suspiciousness of temporal coupling in commits together and optimize for pointwise mutual information, given that our context is the commits, in which files appear together, or these files which are committed by different developers. So we build our concurrence matrix the same way. Imagine that you have developer A and developer B, and this cell of your matrix is how many times they committed to the same file, summed by all the files they ever touched. Then you apply Swivel, already existing, very nice tool. It works quite fast. And you get your embedding, and this really works. However, there are some problems with this. You need to find the optimal vector size, and vector sizes less than 50 are usually bad for convergence. You have to wait some time until your algorithm converges. Also, if you have less than 10,000 samples, and usually you have less than 10,000 samples, it's quite unusual to have so many developers in your project, right? 10,000 is a big number. Or files, 10,000 files in your repository is quite a big number, right? So in this case, convergence is also not so good as on the large scale, unfortunately, but it's still convergence. Finally, if you have less than 100 samples, the GPU becomes useless. You have no acceleration. There is no point of accelerating matrix multiplication of such small matrices. You get no benefit. Apart from that, it works. What can you do next? You can apply t-SNE or UMAP to visualize these embeddings, to map them to 2 dimensions or 3 dimensions, and look at them by your eyes, to analyze them, to see that, okay, these files or developers are together, so maybe something is interesting about them. You look inside and read the metadata and draw some conclusions. This is how it may look like. It is plotted for the Linux kernel and TensorFlow projector. You see that all the files which are related to NVIDIA open source driver, although they can be in different directories really, they are near each other, and t-SNE maps them to roughly the same spatial cell, which is cool. The second example is related to lines and diffs and all these things. The concept is like this. Imagine that you have a file in Go. Who heard about Go? Good. Well, it's not so really important, but anyway. Imagine that you have a file foo.go and you add it in 2014, and it's quite a simple file, just has 3 lines. In 2015, you add a new function to your file. And in 2016, you edit your 2 functions and also add the 3rd line with the const declaration of x. You can plot how many lines which were created within a certain time period are still not overwritten through the future time. So the yellow band corresponds to the code which you created in 2014. In 2015, you still have 3 lines alive. This is why the line is straight. But in 2016, you edited 1 line which was yellow. And now you have only 2 yellow lines, and you plot exactly that. You see that it starts going down. The same about red and the same about blue. And this type of plot is called a burn down plot because it can only monotonically decrease, and it indicates how much code in your project is still alive, let's say still not overwritten through time. You can plot it for arbitrarily large projects. For example, this is plotted for the Linux kernel. You see that roughly the source code of the Linux kernel, which was created before 2006, when Git was introduced, is twice as less by 2019. So roughly half of the kernel is overwritten. Of course, this is a very rough estimation because, line changes can be different. Maybe you renamed a variable or, did something which is not really touching the logic of the line. So this has its own limitations, but still this is a nice approximation. You can plot it for, these hipster JavaScript new frameworks, and you will discover that in these hipster frameworks, half of the project is overwritten every 6 months, which is a good indication of a bad architecture. You usually should not rewrite half of your project every half a year, right? This is not good. Okay, but we are on the mail conference, right? So we want something more advanced than just plotting these stats. And Eric Bernardson, in his blog post called Git of Theseus, in the end of 2016, proposed to improve this, make it more scientific by plotting Kaplan-Meier survival analysis estimation. So Kaplan-Meier is an extension for cohort analysis. It's more powerful. The awesome thing about it is that it allows you to, let's say, approximate 4 time periods which you haven't really seen. This is plotted for several open source projects, and I think this is for AngularJS, which was overwritten in 6 months or so. So you can estimate the half-life of your code looking at this plot. All right. You can track the ownership of your lines apart from the dates they were created or overwritten. Imagine that you add 100 lines in 2014, but from these 100 lines, half was overwritten in a few years. So you can plot it. The machinery is exactly the same, but you also include the ownership. This is an example from ember.js, JavaScript framework. And I took it because I used to work with a core contributor in ember.js, so I could have some, validation of my insights, and he indeed proved my concerns. You see that there are 2 people here which suddenly become quite big owners of the code base in 2014, and indeed there were 2 these guys, and everybody was afraid of them because nobody could touch their code, nobody understood it. And this is a problem because your bus factor is 1 or 2 in this case. You cannot make big changes to your code base. And there was even a website which was called Who Knows the Core of Ember.js. You can go to it and you get the huge number, and I think it was 2 or 1, something like this. So, yeah, this is how it works. By the way, the dashed area corresponds to contributors which were not included into the legend because there are many people who work on the project. However, this ownership estimation is quite crude. You should not rely just on this plot to estimate the ownership. Why? Because it doesn't take into account your efforts. Imagine that you bombard the project with your commits, you change a lot of stuff every day, you are actively working on it. However, if you just snapshot how many lines you own, you will not own so many, just because you will overwrite a lot of stuff, overwrite yourself. So, should you be considered an owner in this case? Probably yes, because you work so much on the project, but this plot will not indicate it. It will show that you own very little amounts of lines. So the good ownership estimation should take care about your efforts and also about the blame information, and also probably should weight decay by time because you're not interested in what happened like 2 years ago. The project has changed so much that nobody cares about your knowledge 2 years ago. So actually the proper buzz factor and, let's say, core ownership estimation is hard, and we are still struggling to find a good balance. Another example of this line and ownership thingy is that you can plot the matrix of overrides. Imagine that you wrote 100 lines, and from this 100, 20 was overwritten by developer A, another 10 was overwritten by developer B, 50 was overwritten by developer C, and so on and so forth. And this is exactly what is here. So the row is the developer who wrote the lines, and the columns indicate how many lines were written by the corresponding developers. So, Wikipedia, there is a term in Wikipedia, I think it's called edit wars, when people, combat with each other by overwriting each other. So in theory, this plot should reveal that if you have developers who conflict with each other and cancel their mutual changes. However, let's remember what we had in the first example, that as long as we have the similarity matrix or occurrence matrix, we can embed it and visualize it. So we can do exactly that. And it turns out that you can easily capture the core contributors by doing that. They are very nicely grouped in the same cluster after t-SNE or UMAP, doesn't matter. This is plotted for Wireshark. This is traffic sniffer, can do many other things. So all these people in this cluster, they often overwrite each other, and they also overwrite very much. So this is why they are grouped. And the rest are, let's say, casual people who contribute from time to time. And I bet that this will also work for enterprise projects, but I didn't check. Finally, you can also estimate line importance. So this is an example. Imagine that you have this code snippet in Python, and when you do import sys, usually you don't pay much attention to that because sys is a system package, it's well known. However, if you do import of some very rare Python package, probably there is something important about it. If you have the function declaration, you just look once at it. You look at the name, maybe you look at the variables, but it's not so important, right? You can rename your function, and the meaning will be kind of the same. The same about logging, and the same about comments. Of course, you read them, but if something changes there, you will not care as much as if something changes in the if condition. If somebody changes 50 to 49, this will change your program logic. Or if somebody changes the complex condition to some other function call, this will also dramatically change the behavior of your function. So this line is probably the most important in this code snippet. And also return 50. Using magic numbers is bad, of course, but this is a tiny example, so I could not declare a constant. And returning just 50 is, again, a bit important. So if somebody changes to return 51 or 49, the behavior can change, so you should pay attention to that. The question is, how can we estimate the importance? And we can go with machine learning, or we can define a number of rules on the AST level. We are not sure what is the best approach. We are actively studying it. But as soon as you have this black box, which is able to map the importance for each line, you can apply it to diffs to understand whether the diff changes important parts of your program or not important, and do commit classification. So this will help maintainers to prioritize their work. Maybe you heard about this story with Linus Torvalds, who in his early days of working with the Linux kernel had a lot of patches sent to him by email, and he had to review all of them. And sometimes he saw huge patches and he thought, whoa, no way I will review such huge patches, and he just ignored them and didn't respond to the letters, just did nothing. Just because he knew that at some point, if the patch was really worth it, the person will ping him again to ask to review the patch again. If he had this tool, he would be able to quickly assess the, let's say, hardcoreness of each patch. And even if the patch is huge, probably it doesn't change so much, and he could review it, and the other side could be happier. Who knows? The third example is time series, and this is the biggest part of the presentation. Okay, I will illustrate the idea on this example. This is a list of core CPython contributors, sorted by the number of commits they did to the project. Number 2, number 4, number 6, 7, 8, 9, 11, and 12. Somebody is missing. Guido is missing. He is actually number 1, but I did it just for the clarity to illustrate the idea. If you look at the contributors, well, you can, rank them by this number of commits, but it doesn't show you that much as you would probably want to see. However, if we sort them in a certain way, you will have a better insight of what's happening. And I believe this is not very clear because these GitHub commit plots are quite small, so this should be better. You see that I group people so that pairs who worked roughly during the same time period are near each other. Jack Johnson and friend Drake, they both started in 1996 and they both ended in 2004 or 2005. The next two guys, they started in 2000 and they ended in 2012. This happens. Open source contributors come and leave. This is very common. It's quite hard to work on an open source project and don't, have anything in return for longer than 10 years. You need to be really determined about that. So the fact that they managed to work for 12 years is very, let's say, honorable. The third pair began in 2008 and ended in 2016, and the last one, they are still actively contributing. So after sorting your contributors like that, you see that actually only 2 guys are actively working on your project right now. Only 2, not 8. From the initial picture, you didn't have any clue. You had to, look at each person by hand and analyze it, which is hard. So how can we do that? Oh yeah, this is the use cases list. So we can use this clever sorting to estimate how many active contributors you have. And also you can analyze for how long they usually stay in your project, how many years or maybe how many months. And also for the enterprise, this feature is useful because usually you work in the same team, and if you see that several persons work in the same time period, probably they worked with each other and they share some knowledge, even if they didn't commit to the same files as uncoupling. So you can ask any of them what happened 8 years ago, and probably you would get an answer. Probably you would not, who knows. So how can we do that? This is the plan. First, you need to define the distance between your time series. Then you need to apply some algorithm to order them by the difference in the distance. This is for one dimension, so that you can get a flat list, as I had in my example. But also you can try to cluster them in higher number of dimensions, in 2 or 3 dimensions, and also query for nearest neighbors. So this is like the enterprise use case I said a few moments ago, when you ask who is a group of people who worked during roughly the same time period as this, example person. Okay. Now let's try to define the distance. And the brute force approach to that would be just, compare time series by Euclidean distance. It will not work so good, unfortunately, because in this example, the difference will be exactly the same. It doesn't take into account how close are these two explosions in your commit activity. They will be the same. Just by the definition, Euclidean distance works. So we need to be smarter. And it turns out that the standard way to compare time series is dynamic time warping. The algorithm was suggested in many years ago, probably in 1970s or like that, when there were first experiments with speech recognition. Dynamic time warping is good because if you have, let's say, two waves for different speakers who speak with different speed, you still map them to kind of the same template, which was very important for speech recognition. In our case, we can also use it. So the idea is to map each point from the first series to some point at the second time series, so that the sum of the distances is minimal. So we solve an optimization problem. The complexity of this optimization problem is quadratic. It could be worse, of course, but imagine that you want to compare all time series to all time series. You will get cubic complexity, which is ouch. So you would want to reduce the complexity. And there is an algorithm called fast dynamic time warping. It's an approximation which just takes a window around each time point and tries to map it to other time points. It doesn't provide you the most accurate result, but it's good enough for our use case, so we can use it and reduce the complexity to be linear. If you want to calculate it in Python, you can use fastdtw package. It works properly, I checked. And when you compare all time series to all time series, you get your matrix, and it will be quadratic complexity. However, you see that the distance is in quotes. That's because, unfortunately, dynamic time warping is not a proper metric. It doesn't satisfy the triangle inequality. This means that if this AB plus BC, it's not necessarily longer than the AC distance in the triangle. And in turn, this means that you cannot apply TSNE or UMAP or a series of other clustering algorithms which have clever optimizations which leverage the triangle inequality, such as KD trees or ball trees or other trees. You have to do something to please them. Well, for one-dimensional case, however, we can ignore it and work on this so-called dissimilarity, not distance, but more precisely dissimilarity matrix. And we will not even need any sort of this, clustering, TSNE or agglomerative or whatever. And I will present you the very nice technique which I learned 2 years ago from a blog post. Not many people heard about it, unfortunately, but it works really awesome. I really like it. So imagine that I have a photo in red and blue tones. This is what the person chose in his blog post. And the photo was distorted. Every row was randomly shuffled, and every column was also randomly shuffled. This means that all pixels which were on the same row, they are still on the same row, but the row is shuffled. And the same about the column. So you cannot see anything on this, right? And if you apply any conventional clustering algorithm, such as agglomerative clustering or optimal leaf ordering, you will get something like this. So you'll have some locality regions of more or less similar pixels, but you will not get the original photo. You will not be able to recover it. However, it is possible to recover, surprisingly, and this is how it looks like. This is Nicholas Krutchen in his blog post. So he applied the technique called seriation to recover the original photo from these shuffled rows and columns, which seems impossible, but it's possible. The seriation works like this. You define your problem as the optimization problem, where you minimize the sum of pairwise distances. So for every row, you calculate the difference, and for every column, you also calculate the difference. And then you find the optimal ordering in which the sum of pairwise distances is as small as possible. And if you think about it, it will remind you of the traveling salesman problem, where you have cities, and you have the salesperson who travels around these cities so that his path is of minimal length. It's exactly the same formulation of the problem. So it's well studied. There are, well, it's NP hard, of course. It's not so good, but there are some libraries which work on quite big number of cities or nodes. And we apply it, and we get that. This is how seriation works. We solve the traveling salesman problem and get the result. Byte to byte, pixel to pixel as the original image. Seriation is good if you want to sort your heat maps. For those of you who are data scientists and plot heat maps often, try to apply seriation. Probably it will work better than agglomerative clustering. Not always. It doesn't always work better, but sometimes it works dramatically better. The implementation is in Python package called seriate, which also in turn delegates the heavy lifting to Google operational research tools for solving the traveling salesman problem. As you may know, Google has Google Maps, and you have routing and Google Maps. Actually, it's open source, and this is what's inside. Okay. Once you are able to sort your points in one dimension so that you seriate them, the final step is to find the groups of similar items. If you do this with developers, with commit time series for developers, you would want to group developers by similarity of their time series and also to detect outliers. In my toy example, I did it for you by hand, but you don't want to do this by hand. HDBSCAN is a no-brainer clustering algorithm for that. It doesn't really require you to tune anything. It doesn't require you to set the number of clusters beforehand. Compared to DBSCAN, it doesn't require you to specify the alpha. So it just works. Well, it has some hyperparameters, but they don't change much of the things. And this is how it looks like when you apply it to TensorFlow contributors. You see that their bot, TensorFlow Gardener, which synchronizes with internal Google code base, it's an outlier. It was as an outlier exactly as we wanted. We see that the number of core maintainers who joined the project in the early days and are still active are marked with red by DBSCAN. 3 core maintainers who used to be very active in the beginning but no longer work are also put in the same cluster. Then you see that people join the project again and again from time to time, and you see that you have, for example, these four guys who joined recently and are actively working. So this works like that, and you can use it to estimate how many people are working on the project right now and how it evolved. And I cannot say this is the core team estimation, but again, this is another approximation of that. So this is for one dimensions. As I said, you can also try to map it to a higher number of dimensions. However, this triangle inequality is really preventing you from doing it correctly. It turns out that in practice, it's not so important that you have a dissimilarity matrix and a distance matrix, so you still get some decent result, but it's dirty. It's not theoretically proven to be correct, and just by the way t-SNE or UMAP work, they do it in the wrong way, so you don't get, let's say, the precise embedding. But still, you can do that. You get some more or less fine result. If you query for nearest neighbors and you want to do this in the embedding space, you don't want to carry this huge dissimilarity matrix with you every time. 14 dimensions with UMAP is usually enough to have 85% of nearest neighbors preserved, which is quite fine. We are fine with that, so this is okay for the production. I'm finished with the third example, and the final part of my presentation is devoted to tooling. The thing which I want to emphasize about the tooling is that it's very advantageous to work with regional data in the regional format. If you have Git, you would like to work with Git repositories directly and not, put them into database first and then work with the database or something. This is related to data lake concept. Who heard about data lake? All right, so the data lake is something which contains your data in the original format. The same is about development history mining. You work with your code in the original format, in Git repository format, and not try to convert it to something else. As soon as you try to convert it, then the repository will be updated, and you have to sync it to your own format, and you will have a lot of useless complexity, which you can avoid. I will present two tools. The first is named GitBase. It works with Git repositories directly, exactly following the code lake paradigm, and it allows you to run SQL queries on top of your Git repositories. It is Git native, so it understands all the Git concepts, how Git works. You have different types of objects, blobs, commits, etc. It understands everything, and you can write any complex SQL with nested selects or any crazy joins to extract the information that you want. And this works not for one repository, but for many repositories as a whole. So it's very useful for, let's say, high-level mining. GitBase is integrated with Babelfish, which is an open source parsing server. It exists for one particular reason. You would want to write code once and run it on any programming language. If you want to extract all the functions from Python, from Go, from C++, from Java, you don't want to write this extraction for each language independently. Java has one AST format, Go has other AST format, Python has a third. You want to write your code once and extract functions from all the languages in one line. And GitBase allows you to do that through Babelfish. So thanks to the universal abstract syntax tree format, you can write something like this. You want to extract all import paths from source code files, and this just works. In this snippet, I extract all import files from Go, but I can easily omit this line, and it will still work, but for all the programming languages, if you need it. This is quite nice. The second tool is called Hercules. It always works for a single Git repository, so you cannot apply it to large scale easily. However, it's much more hackable because it contains a directed acyclic graph of atomic analysis inside, which you can hack arbitrarily as you want and experiment with any development mining. At the bottom, it has the Go implementation of Git. It appeared 3 or 4 years ago, so many lessons were learned since the C implementation of Git. And it's much more mining friendly than using, cgit directly or libgit2 or any other Git library. It was one of the intended use cases. And for data analysis, Hercules delegates the work to Python. So if you know Python, you can just use Hercules as a feature extractor and do something on top with Python, which is great because Python is well suited for all this data analysis. Examples of how you can apply Hercules: you This is a command line too, so you have to code in command line. You run Hercules and then the type of analysis you want to extract, and then you run the Python script labels and plot. So all these three examples which I presented before, they were actually created with Hercules by these three simple commands. So there is no hardcore code which you have to write to reproduce the work. Datasets are included into the tooling just because sometimes you want to analyze many repositories and a big amount of source code. And cloning from GitHub is not so easy as it may seem. Believe me, if you want to clone 100,000, you will be rate limited. You will get failures. You get network failures. Something can go wrong with your hard drive. So this is where big data starts. And as soon as big data starts, you get unique challenges which you didn't have at small scale. So you will have to address them if you do this by hand, by writing a shell script which runs git clone or something. Instead, you can download the dataset and avoid all these problems. Sometimes you even don't need the whole Git repository, but maybe just the graph, which I showed in the introduction. Commits, authors, how they are mixed with each other. And I will present it in a minute, but one final note about the datasets is that since several years ago, we have new laws in Europe, GDPR, you certainly heard about it. And Git is in a sort of gray zone because every commit has some personal information embedded, right? You have people names and you have emails. And it's publicly available, and actually nobody, gives an explicit consent that they are fine with their personal data to be stored in a Git repository. It's not automatically anonymized. Also, GDPR makes you to provide a way to remove your personal information by request. If you do this in Git, it's just impossible because all your hashes will change, everything will change, and you'll get completely different Git repository. And you will have to force push or do other nasty things. So it's completely GDPR unfriendly. And as we see, we have no issues with that right now. But as soon as you compile a data set, for example, a graph data set where you store all the authors and the commits, you'll get into trouble because the personal information will be easily available. At least for Git, you have to do many additional steps and parse it for every Git repo, and you need to clone them. It's not easy to compile, a full database of all open source contributors. Although I know some companies did it. They even had their MongoDB database left open in Barcelona, so it was very bad. Anyway. As soon as you release this data set, you have to anonymize it to conform to GDPR. And this sometimes, limits the possible use cases, unfortunately. Software Heritage provided this example of a data set, a graph data set, where they have everything but the source code. 85 million repositories with more than 1 billion commits from them, all in a very nice graph structure and also anonymized, obviously, in two formats, and PostgreSQL and then Parquet. So you can download it. As far as I remember, it's several terabytes, and you can play with it. You can, calculate PageRank or whatever you want. It's possible. The second data set is called Public Git Archive. It's more to the data lake story of things. It contains not so many repositories, only 260,000. However, this is just raw Git pack files, but also with forks inside. They are deduplicated. If you want to clone them by hand, you will fetch roughly 3 times more data as in this data set, which is nice. Why 260K? That's the number of repositories we had in early 2019, which had more than 50 stars on GitHub. This is our approximation of popular source code. We all know that this is not really related to, how good is the source code itself, but, we had to threshold. We could not clone all 90 million of GitHub repositories. It's too much for us. So you can go to PGA source tech and download this data set and again play with it. There is a paper about it as well. So I'm passing over to the summary, and I think it's good timing. To summarize, if you want to do something with similarity matrices, occurrence matrix is one case of the similarity matrix. You can apply Swivel or Glove or any other algorithm to embed it, and embeddings will provide you rich insights. If you have a distance matrix or dissimilarity matrix, which you can roughly treat as a distance matrix, you can apply TSNE for a small number of dimensions, and also you can apply UMAP, which is newer and sometimes works better. And for sure, according to our experiments, it works better for more dimensions than 2 or 3. If you have sequences or heat maps, apply seriate. You will not regret it. It will work very, very nice. You can compare it to agglomerative clustering. Most likely you will get the same result or worse. And finally, mining software development history is much fun. I showed you 3 examples. You see that there are some real use cases where they are helpful. So we're ML engineers and data scientists who work with code every day. How about, applying our knowledge to how we do our job, some meta improvement of things. We can certainly do that. So before finishing, just 2 more slides about the resources if you are interested in the topic. The first is the book written by Adam Thornhill, from which I took some of the ideas for the examples I presented. It's called Software Design X-Rays. It's a really nice book about how you can mix psychology and development together, and also some mining elements. So it's really nice. And the second is about the academic conference called Mining Software Repositories. It had more than 20 issues, so it has a long history. Used to be a workshop in ICEC. They have an official website, msrconf.org. They publish papers every year, and it's pretty much related to what I presented, to mining software development history. It's very nice, it's very fun. Check it out. That's all I wanted to say. Here are my contacts. Follow me on Twitter, Vadim Learning, and the presentation is available online. Thank you very much.